Hey there, science fans! Today we're diving into the fascinating world of thermofluid systems, specifically those used in air conditioning and refrigeration. Thermodynamics is all about heat and how it moves, while fluid mechanics focuses on how fluids, liquids and gases behave in motion. How do these fields come together to keep us cool on a scorching summer day? It's all about using a special fluid called a refrigerant that can easily absorb and release heat as it changes state from a liquid to a gas and back again. By manipulating the pressure and temperature of the refrigerant, we can control the flow of heat and create a cooling effect. In an air conditioning system, the refrigerant acts as a heat courier, picking up heat from the warm indoor air and transporting it outside, where it's released into the environment. This continuous cycle of heat transfer is what keeps our homes, offices, and even our ice cream from melting on a hot day. Let's break down the different components of a typical air conditioning system and see how they work together to create a comfortable indoor environment. The four main players are the evaporator, compressor, condenser, and expansion valve. The evaporator is where the magic happens. It's located inside the building and contains the refrigerant in its liquid state at a low temperature. Warm indoor air is blown over the evaporator coils, and as the refrigerant absorbs heat from the air, it evaporates and turns into a gas, cooling down the air. The now gaseous refrigerant then travels to the compressor, which increases the pressure and temperature of the refrigerant vapor. The hot, high-pressure refrigerant then flows to the condenser, usually located outside the building, where it releases its heat to the cooler outdoor air, condensing back into a liquid. The fan you hear whirring away on the outside unit helps to dissipate this heat more efficiently. Finally, the high-pressure liquid refrigerant passes through the expansion valve, causing a sudden drop in pressure and temperature, bringing the refrigerant back to its initial low-temperature, low-pressure liquid state. This cycle repeats, keeping your indoor environment cool and comfortable. Now that we have a basic understanding of the components involved, let's dive a little deeper into the thermodynamic cycle that makes it all possible. The refrigeration cycle is a continuous loop that involves changes in pressure, temperature, and state of the refrigerant. We can visualize this cycle on a pressure enthalpy diagram, which helps us understand the energy changes taking place. As the refrigerant absorbs heat in the evaporator, its enthalpy increases, but its pressure remains relatively constant. In the compressor, the refrigerant's pressure and enthalpy both increase as it's compressed. The condenser stage is where the refrigerant releases heat and condenses back into a liquid, resulting in a decrease in enthalpy at constant pressure. Finally, the expansion valve causes a drop in both pressure and enthalpy, bringing the refrigerant back to its initial state, ready to absorb more heat. The efficiency of a refrigeration system is measured by its coefficient of performance, or COP, which tells us how much cooling we get for every unit of energy we put in. To truly understand the inner workings of a thermofluid system, we need to crunch some numbers. Let's consider a simple example to illustrate how we can calculate the cooling capacity of an air conditioning system. Imagine we want to cool a room by 10 degrees Celsius, and the rate of heat gain from the surroundings is 5,000 watts. This means that the air conditioner needs to remove 5,000 joules of heat energy every second to maintain the desired temperature difference. To determine the refrigerant flow rate required to achieve this cooling capacity, we can use the following equation. Q equals M underscore dot times H underscore 1 minus H underscore 4. Where Q is the cooling capacity, which is 5,000 watts, and M underscore dot is the mass flow rate of the refrigerant. By knowing the enthalpy values for the specific refrigerant being used, we can solve for the mass flow rate. This value tells us how much refrigerant needs to circulate through the system per unit time to achieve the desired cooling effect. Furthermore, we can analyze the pressure drop across different components, such as the evaporator and condenser, using fluid mechanics principles to optimize the system's design for better efficiency. So, there you have it. We've explored the fascinating world of thermofluid systems and how they keep us comfortable year-round. From the basic principles of thermodynamics and fluid mechanics to the intricate workings of the refrigeration cycle, we've seen how these systems rely on the precise interplay of heat transfer, fluid flow, and phase changes to create a cooling effect. Understanding these concepts is essential for designing and optimizing air conditioning and refrigeration systems, with far-reaching implications in various fields like power generation, chemical processing, and aerospace engineering. Thank you for your attention. This was done by Ahmed Al-Attas, matrix number 2310600205 for Principles of Engineering Thermofluids, subject assignment 1.